Up to last class, we have completed talk on the dipole, right? The last topic was torque acting on the dipole. So we have even discussed SHM, simple harmonic motion, angular SHM. There was a homework question, I guess. I gave a homework question, right? Yes, sir. Okay. So did you completed that homework question? You were supposed to prove that motion of, okay, then just check your answer. Motion of electric dipole in uniform field uniform electric field is SHM. So you were supposed to prove that motion of this dipole in a uniform electric field is SHM. So to prove this, let's consider a uniform electric field. Consider a uniform electric field E. In this electric field, let's place the dipole. This angle is theta. If I place this dipole in this uniform electric field, this dipole will experience a torque, and due to that torque, this dipole will start rotating. It will rotate and will try to align itself along the field. A torque will act on the dipole. Torque Pe sine theta will act on the dipole, and this torque will try to rotate this dipole and will try to align the dipole in the direction of it. Now, as soon as this dipole becomes parallel to electric field, the net force as well as net torque becomes zero. This dipole should come to rest, but it will gain enough momentum to overshoot its equilibrium position. So a torque acts on the dipole. As soon as dipole becomes parallel to field, the net torque on the dipole is zero. It overshoots its position. It overshoots its equilibrium position. Then again a torque will start acting on it. Afroza, what should be the direction of torque in this case? Earlier this was clockwise. If a dipole comes in this position, this is the orientation of dipole. What should be the direction of torque? Right? It should be anti-clockwise. Anti-clockwise means it will again try to align itself in the direction. And it will again overshoot its equilibrium position and come to this position. When the dipole comes to this position, again a torque will act on it. It will try to align it along the direction. So this dipole will keep on oscillating about the direction of electric field. So dipole will oscillate. The restoring torque that will act on the dipole acting on dipole tau is Pe sine theta. So this Pe sine theta is the restoring torque which is acting on the dipole. Now since this torque is restoring, this is restoring in the sense it will try to align dipole along the field. So since this torque is restoring, I am putting a negative sign over it. This negative sign simply tells that the torque acting on the dipole is restored. In the next case, so is it equation of SHM? Jubena, what is the equation of SHM? We have discussed in the previous lecture.
PE.
Equation of SHM was minus of k theta, right?
K theta.
Equation of SHM, equation of simple harmonic motion. So to prove that a system is in SHM, you have to prove that tau is equal to minus of k theta, where k is some constant. But here it's not theta, this is sine theta. So if sine theta comes in this equation, it's not SHM. It's not SHM right now. This is oscillatory. Dipole will oscillate. Dipole will oscillate about electric field. Dipole will oscillate about electric field. It will keep on oscillating about the field, but that oscillation is not SHM. For an oscillation to be SHM, it should satisfy this equation. That means torque should be proportional to theta. But here torque is not proportional to theta, it's proportional to sine theta. So it's not SHM yet. But if we consider small oscillation, if we consider small oscillation, that means sine theta is approximately equal to theta. If angle is small, then you can write your sine theta is almost equal to theta. Instead of sine theta, you can write theta. And the equation of restoring torque will be minus of PE theta. If angle is small, then you can write sine theta just as theta. So this is minus of PE theta. This is the restoring torque acting in the dipole, which is minus of PE, which is the equation of SHM. This is equation of SHM. This is the equation of simple harmonic motion. Now, if I compare this with the standard equation, which can be written as tau is equal to minus of k theta. This is equation 1. This is equation. On comparing 1 and 2, you can say that k is equal to PE. If we compare 1 and 2, then we can write that k is equal to P. That this restoring torque k is equal to P. K is equal to P. So the constant of SHM, k, in this case is P. The next step is he's asked, is it clear up to this point? Afroza, Fatima and Jubaina.
Yes, it's clear.
Clear, everyone. Sure. The next is you're supposed to calculate angular frequency. Angular frequency simply means the frequency at which this dipole is oscillating. So the angular frequency simply is its root over k by I, where I is moment of inertia. This is how we calculate angular frequency, moment of inertia. What is moment of inertia? It's rotational analog of mass. The role which mass plays in straight line motion is played by moment of inertia and rotation. Moment of inertia is the rotational analog of mass. So it's root over k by I. Root over k by I. Here k is PE, so you can simply write your omega as omega is root over PE by I. That's omega, it's root over PE by I. Next, you can write your omega as 2 pi by t. 2 pi by t is root over te divided by I. So you can write your time period as 2 pi root over I by p. So this is time period. Time period is 2 pi root over I by p. This is how we write time period. So that's the solution. So if we just note it down. So if the question is what's the motion of electric dipole in uniform electric field, then in uniform electric field the motion of dipole is simple harmonic. It keeps on oscillating. The motion is such. So shall I rub it? Afroza, Fatma. Okay, the next question on electric dipole is discuss motion of dipole. This is qualitative. Discuss motion of dipole in non-uniform electric field. So if field is non-uniform, non-uniform means magnitude or direction of field can vary from one point to another. So let's say this field is uniform. The strength of electric field is E1 here. And in this region, let's say the strength of electric field is U. I placed a dipole. This is minus Q charge. This is plus Q charge. The angle between them is theta. Okay. So what is the direction of electric force on this charge plus Q? Afroza, the direction of electric force on this charge plus Q. Is it along the field or opposite to the direction of field? Force, not torque. Force on this plus Q charge, Afroza. The force on positive charge is along the direction of field. The direction of force on the positive charge is along the field, that is plus QU. And for this negative charge, the direction of force is away from the field. So field is acting to the right hand side, then force will act in a direction opposite to that. That's minus QE. That is the direction. So Fatima, what about the net force? Fatima, what is net force on dipole?
0.
0. Just check your answers once more. Will it be 0?
Yeah, sir, because it's opposite
But,
and
No.
no.
oh yeah, it's
E1 and
it's
E2
0.
are, field is not uniform, so force will not be 0. Force would be 0 if E1 is equal to E2. But here E1 and E2 are not equal. So if they are not equal, then force will not be 0. The force is non-zero, right? Clear?
Yes,
E1
sir.
and E2 are not equal, so force will not be 0. It's not. So if net force is non-zero, that means dipole will have some translational motion. If force is non-zero, then dipole will have translational motion. It will have some translational motion. And torque is P sine theta as ever. So again, the torque is non-zero. So both the net force and the net torque acting on the dipole are non-zero. So this dipole will have translation as well as rotational motion. So in uniform electric field, the net force was zero. When we took the field is uniform, then E1 and E2 were equal, so net force was zero. But if your field is non-uniform, then a non-zero force will act on the dipole. And this force will translate the dipole. It can move the dipole in the straight line. And this torque can rotate the dipole. So dipole will have translation plus rotation. It will have translation as well as rotation. So dipole will move in this way. It keeps on oscillating and just move in forward direction. It will oscillate as well as translate. It will keep on oscillating and we move in horizontal. This will be the motion of dipole in non-uniform. Okay, just note it down. Okay, so let's rub it. The next topic is continuous charge distribution. The next is continuous charge distribution. So up to now, we have discussed about point charge and dipole. But you can have other types of charge configurations as well. Like you can have a wire having some charge distributed over its length. You can have a sheet, a two-dimensional sheet having charge distributed over it. Or you can have a three-dimensional volume. So if we talk about continuous charge distribution, we have three types of continuous charge distribution. The first one is linear charge distribution. The first is linear charge distribution. Linear charge distribution simply means, let's say you have a wire, a very thin wire. If the charge is distributed over the wire, then that distribution is linear. So linear is one dimensional. Or you can have surface charge distribution. You can have surface charge distribution. It's two dimensional. Or you can have volume charge distribution, which is three dimensional. So we have following three types of charge distribution: linear charge distribution, surface charge distribution, and volume charge distribution. So let's start with linear charge distribution. Linear charge distribution. Which is one dimension. So you have a wire, a one-dimensional wire, and some charge Q is uniformly distributed over the wire. The length of the wire is L, so charge Q is uniformly distributed over the wire. Uniform distribution means there are no gap in the wire. There is no gap. Like this wire doesn't break from any point. The distribution is uniform. It's a continuous distribution. It's uniformly distributed on the wire. Uniform means, say, let's understand uniform in depth. Say I consider a portion of 1 meter. I took a portion of 1 meter of the wire and the charge over this portion is 2 coulomb. I took a 1 meter portion, the charge over that 1 meter portion is 2 coulomb. If I consider another portion of 1 meter, then again charge on this portion will be 2 coulomb. If the distribution is uniform, that means on each and every point of the wire, equal charge is distributed. If I consider a segment of 1 meter throughout the wire, then the charge on that 1 meter segment would be same. If it is so, then you will say that charge distribution is uniform. But if I say that, if I consider 1 meter from the left hand side, then over that 1 meter charge is 2 coulomb. But if I consider 1 meter from the right hand side, then the charge is 3 coulomb. Then this distribution is not uniform, this is non-uniform. But for the time being, we are considering only uniform charge distribution. We are considering distribution which is uniform. So we need a term which is known as linear charge density. We will need linear charge density which is represented by lambda. So linear charge density lambda is simply total charge of the wire divided by total length. That's lambda. Lambda is total charge over total. This is how we define linear charge density lambda, total charge by total length of the wire. So lambda is simply total charge divided by total length. But we use this definition only if charge distribution is uniform. Instead of the complete length, let's say you can have a charge delta Q is uniformly distributed over length delta L. So instead of total length of the wire, you have a small section of the wire of length del L, and the charge over that segment is delta Q. So Jubena, what should be the value of lambda in this particular case?
Q2 minus Q1 by L2 minus L1.
Yes, it should be delta Q over delta L. So that is Q2 minus Q. It's always charge divided by length, charge per unit length simply. But instead of this this formula is again useful if your charge distribution is uniform. But instead of uniform distribution of charge, if you have a non-uniform distribution, for non-uniform charge distribution, for non-uniform charge distribution, you can write your lambda as lambda is limit delta L tends to 0, delta Q over delta L, and this delta Q over delta L could be written as dQ over dL. So the lambda in this case is lambda is dQ over dL. So this is the value of lambda. Lambda is dQ over dL. So instead of dividing, you are not now differentiating charge with respect to length. This we use when your charge distribution is uniform. If charge is non-uniformly distributed, then you can't use this expression nor this expression. You will use this one. Lambda is delta dQ over dL. You're differentiating charge with respect to length. And the SI unit of lambda is it's charged by length. So this is simply coulomb per meter. Just note it down, please. Afroza, shall I rub it? Afroza, shall I rub it? So let's see some questions on linear charge density. The first question of linear charge density is a charge of 2 coulomb is uniformly distributed over wire 4 meter. Calculate first linear charge density, second part charge on 2 meter length of wire. You also need to calculate charge on 2 meter length of the wire. So the first part, linear charge density is represented by lambda, which is total charge over total length. The total charge on the wire is 2 coulomb. The total length of the wire is 4. So linear charge density is simply 1 by 2 coulomb per meter. Okay. The second part, charge on 2 meter length of the wire. So delta Q could be written as lambda into delta L. Straight is based on unitary method. Lambda L is 2. Delta L is 2. So lambda is half into 2. So that's simply 1. Basically unitary method. Linear charge density means charge on 1 meter length. If you want to calculate charge on 2 meter length, just multiply it with lambda. If you want to calculate charge over 3 meter length, just multiply it with lambda. So is it clear? Afroza, Jubaina. Solve one more question. Try this numerical. Say linear charge density instead of a constant, say linear charge density is lambda is equal to 2x coulomb per meter. This is linear charge density wire. Calculate charge on 3 meter length of wire. So this 2x, it's uniform or non-uniform? If your charge density is 2x, that means is it uniform or non-uniform?
Non-uniform.
Non-uniform. Here this lambda varies with x. If lambda varies with x, that means your charge density is non-uniform. Charge density is non-uniform. This is AB. So for non-uniform charge density, say lambda is 2x, right? So consider a very small portion of the wire. If your lambda is in terms of variable x, then choose a small element of the wire having length dx. If lambda is in terms of y, then use a small element of length dy. If lambda is in terms of z, then use a small element of length d. So dq is charge on length dx. Charge on length dx. So lambda is dq over dx. So dq will be lambda. Lambda is dq over dx. dq is lambda. To calculate the total charge, just integrate this expression from 0 to 3. Yeah, 3 meter length is given, but here charge density is non-uniform. So Fatma, you just can't simply multiply lambda with 3. This will not give you the right answer. So whenever you have non-uniform charge density, first of all choose a small element. small element of the wire, the variable will simply depend upon the variable that you are using. So if your lambda is in terms of x, then your small element should be dx. If your lambda is in terms of y, then your small element should be dy. If your lambda is in terms of z, then your small element should be dz. So your lambda is simply dq over dx. So dq is lambda dx. Just multiply, just integrate on the sides. If you integrate dq, you will get q. If you integrate lambda dx, so that is 0 to 3, it's 2x dx. Just complete this integral and report answer in chat. Just complete this integral. No, it can't be infinite. No. It's 0 to 3, 2x. Jubena and Afroza, your answers?
Some last.
Okay. Afroza and Fatima, it would be better if you can use mic. That's more engaging. $18. No. Jubena got 9 by 2. Okay. Afroza, your answer? Okay. So means you people are having problem in integration. Although we have discussed integration in that numerical solving workshop. Huh? We have discussed integration. So Q is, it's 0 to 3, 2x dx. Here power of x is 1. You can take this 2 just outside this integral, and this is simply 0 to 3 x to the power 1 dx. Then this q is simply, it's 2. If it is x to the power 1, this is x to the power 1 plus 1 over 1 plus 1. Limit is from 0 to 3. Q is equal to 2. It's x square over 2. Limit is from 0 to 3. Next, you can cancel this 2 with this 2, and the charge is x square, which is 3 square minus 0 square. So the Q is 3 coulomb. So the total charge on the wire is 3 coulomb. The Q is 3. No, sorry, not 3. It's 9 coulomb. You still have issues in it, Afroza, Jubena, Fatma? You all were making some mistakes in it.
No, sir, I forgot to cancel the 2 and 2. That's why.
Okay, if you are lacking something in integration, I will share a recorded lecture over the group of integration and differentiation. Sure. So shall I rub it? Okay. The next is the second type of char density is surface char density. Yes, Afroza, it's uploaded. Yes. The next is surface char density. Surface char density is simply charge surface charge distribution. Now, instead of one-dimensional body, the charge is distributed over a two-dimensional body. So, if this is a two-dimensional body, some Q charge is distributed over this two dimension. The charge distributed over two-dimensional body is Q naught. The surface area is, here we define surface charge density. Okay, Fatma, can you guess what should be the formula of surface charge density? It's similar to that of linear charge density. Instead of length, we just have area. Fatma.
It's uniform.
No, formula for surface charge density. Say charge Q is uniformly distributed on area S. So what should be the surface charge density? What should be charge per unit area, Fatma?
Q by S.
Yes, Q by S. Total charge over total area. But we will use this expression only if your charge distribution is uniform. We will use this expression only for a uniform charge distribution. After surface charge density, the next is if instead of the complete area, we have a small portion of area delta S, then we can define this sigma as just delta Q over delta S. But this is again useful only if your charge distribution is uniform. For non-uniform charge distribution, if your charge distribution is non-uniform, then instead of delta Q by delta S, we can simply use limit delta S tends to 0, delta Q over delta S. This delta Q over delta S could be written as it's dq over ds. So this is sigma. Sigma is dq over ds. Sigma is dq over ds. So this you can use if your charge distribution is non-uniform. And its SI unit is charge upon area. So its SI unit is simply coulomb per meter square. This is the SI unit, which is coulomb per meter square. Okay, just note it down. Okay. Okay. Rosa, shall I rub it? After surface charge distribution, we can even use volume charge distribution. So in volume charge distribution, instead of area, charge is distributed over volume. So charge Q is uniformly distributed on volume V. This is volume. So here, instead of surface charge density, we will just use volume charge density. We represent volume charge density by rho. We represent it by rho. This is charge per unit volume. Or you can write this as delta Q over delta V if delta Q is charge over delta S. So this is delta V. For non-uniform charge distribution, just take this limit that delta V tends to 0. That's delta Q over delta V could be written as dQ over dt. So rho will be simply dQ over dt. So here SI unit is instead of square, it would be Q. So it's coulomb per meter. Please note it down. Okay. So shall I rub it? Sure. Okay, the next is electric flux. So before starting electric flux, see what is area vector. Usually we consider area as a scalar, but to calculate electric flux, you are supposed to convert area into vector quantity. The direction of area vector, direction is perpendicular to surface. Direction of area vector is perpendicular to the surface. It's perpendicular to the surface. So this is S. This is the direction of area vector. That's it. It's always perpendicular to the surface. So if you have XY plane, then direction of XY plane will be perpendicular. Let's say if I'm taking this particular surface, I'm saying this is my area, then direction of area vector will be perpendicular to it, either upwards or either down. This is the direction of area vector, either upwards or it will act either in downwards direction. So area vector S is S in cap. This is area vector, which is S in cap. Its direction is perpendicular to surface. So electric flux, now we define electric flux. Electric flux is number of electric field lines, number of electric field lines crossing an area normally. So the number of field lines which is crossing an area normally is known as electric flux. Let's say I consider this particular area and 3 field lines are passing this area normally, then the flux would be 3. We represent flux by 3. 5 will be 3. So electric flux is simply just count the number of field lines which is crossing the area normally. Then you can get flux. But instead of field lines, if you have field, if you have electric field. So Jubena, what is difference between electric field and electric field lines? Jubena. Difference between electric field and electric field lines. So the difference between them.
Electric field is the area surrounded by those lines.
Okay. And what is field lines?
Direction.
Okay. In field and field lines, which is the physical reality? What physically exists? Either field exists physically or field lines exist, or both. Yes.
Field lines.
Field lines. Okay. Afroza. What's the difference between field and field lines? And which one of them are physical reality, which exists physically? Field, right? See, Jubena, electric field is the physical reality. If you take a point charge, then around that point charge, electric field do exist. Electric field is the physical reality. But electric field lines are simply some geometrical construction. Field lines are some simple geometrical construction that we would use to represent electric field. Field lines are just simple geometrical constructions. So the physical reality is field. This is the physical reality. Electric field is the physical reality. And field lines we use that. So in terms of electric field, electric flux. So if field lines are given, then simply just count the number of electric field lines, that is flux. But if you have field, let's say this is the area. Fatma, what should be the direction of this area? So you have some areas. What is the direction of this area, Fatma?
Perpendicular to this surface.
So this is the direction of this area. And say this is the direction of field. This is electric field E. Angle between electric field and area vector is theta. So theta is the angle between electric field and area vector. Area vector means perpendicular to area. So angle between perpendicular to area and electric field is theta. So you can define electric flux phi as the dot product of electric field and area vector. You can define your electric flux as the dot product of electric field and area vector, it's E dot S. Or you can define your electric flux as ES cos theta. This is the definition of electric flux if you have field. But if you have field lines, the flux is simply just count the number of field lines, that is. Okay, Afroza, can you guess the SI unit of electric flux? Can you guess the SI unit of flux? Jubena. SI unit.
CM square.
It should be what?
CM square, coulomb meter square.
It's unit of field multiplied by unit of area. Na? Unit of field, Newton per coulomb. Unit of area is meter square. So it's Newton per coulomb meter square, or there's one more unit of field which is in terms of volt. So that's volt per meter multiplied by meter square. So that will be volt meter. So the SI unit is Newton per coulomb meter square, or it's volt. This is the SI unit of electric flux. So these are two units of electric field. Flux either Newton per coulomb meter square or simply volt. Please note it down. Then we'll do some numericals over it. Okay. Is Afroza, shall I rub it? Okay. The next is, let's start with some questions. Electric field of 2 Newton per coulomb exists in space. Calculate flux through an area of 5 meters square. Flux through an area of 5 meters square. Electric field lines are inclined at 60° or 30° with plane of area. Now see, this is your area. This is area vector n cap. This direction is the plane of area. This is the plane of area. This is plane of area. If I consider this area, then this is the plane of area, right? This is the plane of area. This is the plane of area. And this is electric field E. This is net electric field. Angle is given with the plane of area, not with the normal. So if the angle with the plane of area is 30°, can you guess the angle with normal?
60°.
60°. It's perpendicular to the area. So this angle should be 60°. So when you calculate flux, you would use that phi is ES cos 60. Just substitute their values. Here E is 2, area S is 5, cos 60 is half. So you can just cancel them out. So phi is 5 volt meter. Phi is 5 volt. So that is the flux. Just one more numeric. Say an electric field E equal to 2I cap plus J cap plus 2K cap Newton per coulomb exists in space. Calculate electric flux through an area of 2 meters square in XY plane. Okay, so can you guess if your area is in XY plane, then what should be the direction of that area? It's an open question for all. So if your area is in XY plane, then what should be the direction of area? In which, along which axis is the direction of area? Jubena, Afroza, Padma. If your area is in XY plane. Yes. No. Area will be, the direction of area will be along a single direction. So if your area is in XY plane, say this is XY plane, this is your area. And if I draw perpendicular over this area, then perpendicular will come out. Right? If your area is in XY plane, then perpendicular to the area would be outwards or inwards. It will be either outwards or inwards. So direction of area vector is perpendicular to the area. That means along Z axis. Right? If area is in XY plane, then direction is along Z axis. What is unit vector along Z axis?
K cap.
K cap. So it would be 2K cap. So flux is E dot S only. So just complete this calculation. This is your electric field. This is your area vector. Just complete this calculation and get the answer. Complete this calculation and get the value of phi. Four K. Four Fatima. So the flux is 2I cap plus J cap plus 2K cap dot area vector. Area vector is 2K cap. So it's 2I cap plus J cap plus 2K cap. If it is 2K cap, so you can write this 2K cap as 0I cap, 0J cap plus 2K cap. Now take dot product. The coefficient of I cap is 2, coefficient of I cap is 0, so it's 0. Coefficient of J cap is 1, coefficient of J cap is 0, so that's 0. Coefficient of K cap is 2, coefficient of K cap is 2, just multiply 2 into 2. So that is simply 4 volt. If you are taking dot product in Cartesian form, just multiply ith coefficient with the ith one, jth with the jth, and kth with the kth. So I'm just multiplying this coefficient of I cap, which is 2, with the 0, j cap, which is 1, with 0, k cap, which is 2, with 2. So that's 4 volt. So that is the value of flux in this case. Is it clear? Proza, Fatma, just please note it down. Afroza, share a bit. Okay, the next is next question. Not next question, just next topic basically. When we solve numericals on electric flux, we came across two types of surfaces. There are two types of surfaces. One is plane surface, and another type of surface is curved surface. Plane surface means it's a type of surface for which direction of area vector is fixed. I'm repeating again. Plane surface is a type of surface for which direction of area vector is fixed. For plane surface, direction of area vector is fixed. Its example include like square is a plane surface. If I consider the square, then the direction of area vector is fixed. Direction is fixed, that means for this point, area vector is here. If I consider area vector of this point, then this will be in this direction. Again, this. For all points, the area vector is acting along z-axis only. The direction of area vector is fixed. If direction of area vector is fixed, then your surface is a plane surface. Square, disc, rectangle. These all are examples of plane surface. Next, you have another type of surface which is known as curved surface. For a curved surface, the direction of area vector is not fixed, it changes continuously. For curved surface, direction of area vector change continuously. So for a curved surface of area vector continuously change. The examples include sphere, curved surface of cylinder. Curved surface of sphere. For example, say you have like this is surface of sphere. If I ask you to draw normal over this point, the direction of area vector which is normal will be here. The simple geometry, if you want to put a normal over the sphere, then that normal is the line joining the center of the sphere to the surface. Normal of a sphere is a line which is joining the center of the sphere to the surface. So this is the normal of this. If I ask you to draw normal here, then this will be the direction of normal. This is normal. Over this point, the normal will be here. So for a sphere, the direction of normal is not fixed. Direction of normal continuously changes. These types of surfaces are known as curved surfaces. For plane surfaces, the formula is straightforward. That flux is simply E dot S. This is for a plane surface. Your angle is fixed. But if you have a curved surface, say you have a curved surface of this form. This is the direction. So, is it clear the difference between plane surface and curved surface? Because calculations will have some minute differences. When you are calculating for plane surfaces, the calculations are quite straightforward. But for plane surfaces, integrals will get involved. The difference is clear between plane and curved surface. Let's see how to calculate flux for a curved surface. Say you have a curved surface and say this is the direction of field. The field is in this direction. This is the direction. This is the direction. Over this point, this is the direction of area vector. 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 So at different points, the direction of area vector is different. So to calculate flux in these type of cases, we don't calculate flux for the entire surface in one step. I'm repeating it again. For the curved surface, the direction of area vector change continuously. So we don't calculate flux in a single step for the entire surface. We first consider a small element ds. We first calculate the flux for the small element ds. Flux for ds. That will be d phi. You can write this d phi as simply as E dot d. First, we will calculate flux for the small element ds. Then, for complete surface, integrate it. For the complete surface, just integrate this E dot. There's one more thing. It's not that usual integral that we are. This integral is not over a length. This integral is over a surface. This integral is known as surface integral. This integral is known as surface integral. This integral is known as surface integral. So please note it down. There's one more thing. If your surface is closed, if your surface is closed, for closed surface, you can simply put an integral over it. It's closed integral of E dot. Just put a close sign. This close sign says that you are integrating over a closed surface. Now, learn some type of surface integrals. See, surface integrals are not part of school syllabus, but we use some surface integrals while calculating flux, or in Gauss law we'll use surface integrals. So I'm discussing just two types of surface integral. One surface integral is over the surface of a sphere. Let's say we have a sphere. The radius of the sphere is capital R. On the surface of sphere, I'm considering a small element ds. If I ask you to just integrate this ds, the first thing, can I put closed over here? I'm integrating over the entire sphere. Can I put a close sign over here? Yes or no?
Yes.
Yes, because sphere is a closed surface with a closed sign. Integral of ds means over the surface of sphere, I'm considering infinite number of small elements throughout the surface of sphere, and I'm combining all of them. So can you guess, if I combine all ds elements throughout the surface of sphere, what should be the result? Consider a ball of radius r. I divide that surface of ball into small elements ds. If I combine all these ds, then what will we get?
Volume
Volume.
or area of sphere.
We get area of sphere. And the area of sphere is 4 pi r square. So integral of ds over the surface of sphere is 4 pi r square. Okay, if I do this integral on the curved surface of cylinder, I'm taking just the curved surface, not the ends. I'm repeating again. I'm considering only the curved surface, not the ends. If I do this integral over the curved surface, can I put close sign here? I'm
No.
integrating the closed surface only. No. We can't consider closed sign because the curved surface of cylinder is open. It's like an open pipe. The pipe doesn't have ends. It's like an open pipe. So what should be the result? If I integrate ds over the complete cylinder, it should be integral of ds will be 2 pi r, the total curved surface area of the cylinder. So if we integrate over the curved surface of cylinder, then integral of ds will be simply 2 pi r. So throughout Gauss law, we will use these two types of integrals, one over the surface of sphere and second over the surface of cylinder. Please note it down. Afroza, shall I rub it? So let's do a numerical based on curved surface. We have done two numericals, but they were on plane surface only. Let's solve a numerical on curved surface. So charge Q is placed on center of sphere having radius r. So we placed a charge Q at the center of the sphere. The radius of the sphere is r. Calculate flux through the sphere. Solution. So let's consider a sphere. This is a sphere. And place a charge Q inside the sphere. The radius of the sphere is r. You're supposed to calculate the flux through the sphere. So sphere is a curved surface. To calculate flux, we first consider area ds. The direction of the small area ds is outward small. Now, since your charge is positive, the direction of field is again away from the charge. So see this electric field and n cap. N cap shows the direction of area vector. Both are in same direction. So if we consider flux through the sphere, then this flux will be closed integral of E dot ds, or the flux will be closed integral of EDS cos 0, or your flux will be its closed integral of E. Next, E is the electric field due to this charge at a separation r. So for a point charge, the direction of electric field is Q by 4 pi epsilon naught r square. Fatma, since electric field and area vector both are acting along the radius, they're acting in same direction. So if two vectors are acting in exactly same directions, then angle between them is 0 degree. Here area vector is again perpendicular to the surface, means along radius. Electric field is along the radius, So both are in same directions. That's why angle between them is 0. So if I substitute the value of E here, clear, Fatma?
Yes.
So this is Q by 4 pi epsilon naught R square into ds. So Afroza, what are the constant terms in this integral? Name some terms which are constant in this integral. Q is constant, good. And yes, 4 constant, pi constant, epsilon naught constant, R constant. These all terms are constant. This is the integral of ds. So, Giovanna, what should be the integral of ds in this particular case?
Yes.
What should be the integral of ds? We are integrating over the surface of sphere.
Yes.
Not s, it should be 4 pi r square, right? If you have a sphere, yeah, that is s, but that s in this case is total area of the sphere. That is 4 pi r square. We can divide this 4 pi with this 4 pi, r square with this 4 square, and the result that we get is q by epsilon. This is the flux through the sphere. Now, you have one homework question that instead of r, I'm taking the radius to be 2r and we place a charge q at the same. Now just calculate flux, the value of flux. That's your homework. Can we have a class tomorrow at the same time? I want to finish it up by Friday. I will need 2 more classes to just complete chapter number 1. Then we'll come to chapter number 2. So let's keep one class tomorrow at the same time, 10 to 12 like this. Is it fine for all? Fatma, Jabana?
Yes, sir.
I need at least 3 hours to complete this topic. So one will be on Thursday and next will be on Friday. In the next 2 days, we will complete the first chapter and we'll move on to second. This first chapters are the longest syllabus chapters of history. First and second. So let's stop here. That's your homework. You're supposed to calculate the flux through this sphere. Instead of radius r, I'm just making the radius to be 2r. You're supposed to calculate the flux through this sphere. And the next class is tomorrow at the same time. 10.
Thank you, sir.
Allah Hafiz.